discussing the SONET networks. This is the backbone of communication networks. I mean, different how different cities are interconnected through 48 rings, and it can be one OC 192 that can be the backbone for the national network, and OC 48 rings can be interconnected with the OC 192. Again, the linear chains of OC 12 or the rings of UPSR ring of OC3 channels, how they can be interconnected to the OC48 rings, right? And this linear low capacity channels, sub low capacity channels, they can be in a buildings or in a certain area, small area, like say in an industry or maybe a particular institute, like these things. Right. Maybe intra building can be inter building. These things will be the low capacity rings can be interconnected. And next we have seen this also SONET. This ring can be interconnected with these add drop multiplexings. Add drop multiplexings means you can drop some wavelengths, you can add some wavelengths with ADM devices, and we have seen this ADM device can be implemented using fiber bracketings. Also, we have seen this how these SONET rings are configured in DWDM systems, dense wavelength division multiwave systems. Different wavelengths can also be incorporated here with OC SONET rings. Of course, here before multiplexings, you have to equalize the power of all the channels or the bit streams coming through OC 192. And also in between the multiplexer, demultiplexer, there can be optical amplifiers, post amplifiers, inline amplifiers, pre amplifiers. Those things may be incorporated, right? Next, we have seen this the WDM broadcast and select WDM networks is the most versatile communication network at this moment. And this network, WDM network, can be a single hop network, can be multi hop network. In single hop networks, we have seen this. There is no conversions, electrical to optical conversions, and source to destinations. There will be no conversions, electrical domains. But in multi-hop networks, in a node, intermediate node, there would be electronic optical to electrical conversion is here, right? An example is Sony here. That is four nodes with the star couplers or the bus is there, right? Here, of course, both are single hop networks, and if the single hop networks can be broadcast or can be multicast also. I mean, this node one can send to a particular node, or node one can send the information to all other nodes. So, if all other nodes are then the broadcast, or maybe two nodes out of these two nodes are selected, then it will be multicast. A particular group is there. So this is the single hop network. But in multi-hop network, I mean here single hop networks, the problem is there. Dynamic coordination must be there. That means before transmissions, the receiver must be informed about the wavelengths reaching to that particular receiver. Then only it can tune to that particular wavelengths. Here the problem is the receiver. Each receiver will contain all the wavelengths. Will observe all the wavelengths. So it has to tune the particular wavelength that is supposed to be destined to that particular receiver. So that is a problem here. So it needs costlier equipments like tunable filters, tunable lasers, like these things. Another problem is there is conflict. If two stations transmit simultaneously to a single the same node simultaneously, two different nodes wavelengths, then conflict or this conflict might appear, right? Collision might occur. So to avoid that ones, I mean these problems can be avoided if you consider the multi-hop networks. In multi-hop networks, here each node transmits and receives a particular set of wavelengths. that is shown here, 4-node multi-hop network. Here you see node 1 transmits 2 wavelengths and receives 2 wavelengths, lambda 1, lambda 2, lambda 5, lambda 7. So in this case, you see, I told you last times, if node 1 transmit information to node 2, then directly it cannot transmit. So the first it will transmit to node 3 through lambda 1, which is the common to node 1, node 3, right? And next information, then node 3 will send the information to node 2 through lambda 6. That is it. Right. So in this way, you see, there can be information exchange. So there will be no conflicts or collision of packets in the network. Mm. And each channel is dedicated to a particular. Each channel means each wavelength. Particular wavelength is dedicated to a particular source to destination links. Say node 1 to node 3, a dedicated link is there, that is lambda 1. Similarly, node 3 to node 2, dedicated link is there, that is lambda 6. Similarly, in this way, other links are there. But of course, here, though it can overcome the problems associated in single hop network, but here also, because of these multi hops, a throughput penalty will be there, right? There. That is, if H hops are there, then throughput penalty will be on by H, right? And also in this context, you see header format, it contains source identifier, destination identifier. So whenever there is electrical to optical conversion is here, optical to electrical conversion is here, then the header will indicate where the packet will go. So accordingly, packet will be switched electronically to that specific transmitter. That will direct the packet to the next node in the logical path. So this is the information packet format for multi-hop schemes. And the examples of examples of multi-hop networks. One is SuppleNet. You can see it as SuppleNet is here. De Bruyn network is here. Manhattan Street network. They are the multi-hop networks. Out of this, let us focus on this SuppleNet, which is widely used in optical multi-hop networks. In SuppleNet networks, it is there is a cylindrical arrangement of nodes. Cylindrical arrangement of nodes. There will be k columns and k columns and k columns will be there, and nodes will be p to the power k. If p to the power k, the p will indicate the number of transceivers. Transceiver pairs per node, right? That is p. So if it is k columns and p number of transceivers are there and p to the power k nodes are there, then you see in general the number of nodes in a SuppleNet n can be written as k columns. This p to the power k a particular column nodes. So for k columns, total number of nodes will be there k times p to the power k, where k can be 1, 2, 3 like these things. Right. And total number of wavelengths, total number of wavelengths. If each node requires p number of wavelengths, p wavelengths to transmit informations, then the total number of wavelengths for these n nodes, it will be k into p to the power k plus 1. Right. That is the total number of wavelengths required for a SuppleNet of pk. Here, the SuppleNet, it is denoted as pk. K supplement. Generally, it is written in this way: PK supplement. Well, P represents the number of transceiver pairs, and K represents the number of columns. It is in cylindrical. I'll just show you the examples, then it will be clear. Let us say PK will be 2 by 2. So you have to see how the nodes are interconnected in supplement 2 by 2 supplement. Two by two supplement. You see, that means two columns will be there and two transceiver pairs per node will be there. So you see, this is 2 by 2 supplement. So two columns are there. You can see two columns. This first column, second column. Actually, third column, it is the back of this column 1. Right. I mean, it actually indicates the completion of a trip around the cylindrical from the first column to the destination columns. So actually, these dotted ones, these are actually, this represents the first column, actually first column. So there are actually two columns. Just to show the path here, it is shown in this way. Right. So actually K equal to 2, K columns are there, P transceiver K column, two columns are there. These are the two columns, 1 and 2, and this K plus 1 column, the third column actually it is the back portion, back of this first columns. So basically it indicates the first columns, the last ones. So in this case, how many nodes are there? You can see total number of nodes if you calculate it here. Total number of nodes, you see K into P to the power K. So 2 by 2. So for 2 by 2 supplement, so it is 2 into 2 to the power 2. So total it will be 8. For 2 by 2, it will be, so you can calculate in this way. Right. 8 nodes will be there. Obviously 8 nodes are there. You see 1, 2, 3, 4, 5, 6, 7, 8. So 8 nodes are there. And also, we can calculate the number of wavelengths for two nodes. One here, P means number of fixed transceivers, transmitter receiver, transceiver pairs per node. Right? So here two transceivers are there. For each node, it can transmit two wavelengths. It can receive two wavelengths. Right. So two pairs are there. Right. One pair for transmission, another pair for receiving. Right. So, so we can calculate also. Here it is number of wavelengths. That is number of wavelengths. It is number of wavelengths L lambda. It is P times N. N number of nodes. You have seen it is 8. So and P 2 transmitters 2 into 8. So 16 wavelengths will be there in this case. For 2 by 2 supplements, it requires 16 wavelengths. If particular node it has two transceiver pair. And I think it is quite clear now how can calculate number of wavelengths, number of nodes. Right. You can calculate in this way. And here the important parameter is the average number of hops. Average number of hops between any two nodes. Between any two nodes. What will be the average number of hops? Here, generally, maximum number of hops would be 2k minus 1. 2k minus 1, k is the columns. Maximum number of hops. So 4 minus 1. Maximum number of hops will be 3 in this case. But this simple 8 nodes, it can be 100 nodes, can be 2000 nodes can be there. So number of hops may be quite large. Right. So for these typical examples, if you see connections between say 1 and 5, connection between 1 and 5. How many hops are there? Only one hop is here. You see, 1 to 5, one hop is here. So hop 1. But if you consider the connection between 1 and 7, 1 and 7, then how many hops will be there? 1 and 7. So you see, it can go through 5. It's 1 to 5 through lambda 1, and 5 to 2. 5 to 2, it is actually back portion of the 2. So 5 to 2, it is lambda 10, and from 2 to 7, it is lambda 3. So it can be 1, 5, 2, 7s. This one, 1, 5, 2, 7s. So 1, 2, 3, 3 hops. So maximum 3 hop will be there. If we 2 to k minus 1, that's it. It is 3 hops. For this typical case, maximum 3 hops will be there. Right. There can another option is there. You can see it here. Not only this particular route, it can be also through 6. After 1, it can go through a 6. 1 to 6. You see, 1 to 6 through lambda 2. Next, 6 to 4. Next, you see 6 to 4, because 4 is connected to 7s. So 6 to 4, it is lambda 15s. Lambda 15s. Lambda 15. It is 15 is this one. 16, 15, 12, 14s. So 6 to 4, it is lambda 15, right? And 4 to 7, it is lambda 7. Lambda 7, right? So in this way, also we can have another path is here. Another connection is here, that is 1647. 1647. I think it's quite clear now. So it might be asked for a particular subnet, what is the path? Right. So, but keep in mind the maximum hop can be 2k minus 1. Right. That is 3 hops. It will be there. Right. So in this way, you can decide the connections between a particular node, a particular source node, a particular destination node. Right. And here the average number of hops, I told you that is the most important parameter. So average number of hops, okay, can you here? Okay, average number of hops that can be written in this way: h, that is 1 by n minus 1 sigma of integrate sigma j equal to 1 to k minus 1 j p j p to the power j plus sigma j equal to 0 to k minus 1 into k plus j into p to the power k minus p to the power j. That is our number. These important parameters for a particular KP networks. Particular PK, so PK subunit or PK subunit. P the a pair of transceivers and K is the number of columns. Right. And this is the important parameter. And link also you can calculate NP. How many links here? NP. N lambda I have seen earlier. NP also you can calculate, that is K into P to the power K plus 1. So that will indicate the links, number of links available for this supplenet. And network capacity, they are the important parameters, maybe asked numerically or maybe asked their definitions. Capacity, that is C, actually it is with the dependent parameters involved in the particular uh, parameter. C equal to capacity C, it is K e to the power K plus 1, I mean links, K plus 1 divided by average number of hops. That will that actually indicates the capacity. And per user throughput will be S.